So we'll start, I think, 4-lecture M-Center course of Sergei Gukov from Caltech, which is called Quantum Topology at Generic Q, which kind of nostalgic because when I started quantum group in the 90s, it was algebra, quantum algebra and generic Q. So Sergei, please.
Yes, thank you so much, Jan. It's a pleasure, and I wish I could do it in person. Hopefully one day this will happen, but otherwise it's still good, and I'm glad to see all of you. So first I'll make a few general remarks in this first lecture. So we'll go extremely slowly, or at least that's my intent. So at any point, please feel free to interrupt, ask me to speed up or deviate, and I'll try to give reminders on this point as much as I can. But that's perhaps the first and main kind of announcement I want to make. Also, the way it will work in terms of sharing Blackboard, of course, if we were in one room, we could just use Blackboard. Now we have to use some mock-up version of it. And what I'll use is one of the virtual whiteboards that I like most. Teaching over this past 2 years taught me several useful lessons. And what we'll do is we'll use this whiteboard Fox. I just posted a link in chat. The way it works, you can click on the link, and I'm going to share my screen in real time. So let's see. Just a second. So share screen. Yeah, here we go. So if you click on the link in chat, you should be able to see what I'm sharing on a screen. So there are a couple of navigation buttons. If you click on this compass northwest looking thing, you can move the whiteboard. So let me first write something on it. So I'll write welcome. Oops.
Will we be able to download whatever?
Yeah,
okay, so
you have a link in chat, right? So you clicked on it.
Yeah.
So what will happen is that I'll try to share the screen and then remind myself to move this whiteboard as I'm writing. But the whole point is that if you have the link, you can actually follow it completely independently. So basically, the link will be there. It will outlive many of us. It's going to be virtually in cyberspace indefinitely. So at any point in the future, you can just store the link and it will have all these lectures. So maybe we'll create another one for lectures 3 and 4, but at least for lectures 1 and 2, I'm definitely going to use this one. And also you can refer back to the previous material and so on, again, at your own pace. I'll try to share a screen with immediate part that I'm writing, but you can scroll, navigate your own way. So this is zoom in, zoom out buttons. Move, you click on place on a whiteboard, and then it basically holds it as if with your finger, and you can move around. If you're using iPad, you can use usual 2-finger navigation, zoom in, zoom out options as on iPhone, iPad, and so on. Yeah, so any questions regarding the screen sharing or?
Yeah, and those who are late, they might not see the link which you sent in the chat. So
that's right. So that's actually a good point. So I'll ask Jan, you as a moderator, to maybe resend it once or twice throughout the lecture, or especially close to the beginning, because indeed that's yeah, I cannot see chat and cannot do it myself. Yeah. But please reshare if you.
I just reposted it. And
yeah,
more people join.
Lina has reposted. Great. And so we can write the program in Python, and every second it will repost it. Okay.
Perfect. Yes. So another reason for me doing this is I'll be sharing something else on Zoom. For example, when we get to computational part, I'll be doing computations like this. And again, from teaching experience, I know that when I ask my laptop to handle too many tasks, it collapses. So there is a chance, another kind of announcement, that if network problem or bandwidth of my laptop give up, then I'll probably try to reconnect. I have my iPhone on a standby, but there is an option that on this whiteboard I'll be able to write, because now I'm connected to it and on a different device, and I may still communicate to all of you by writing. Unfortunately, you cannot write back to me, but at least I'll be able to say that my connection is poor or something like that. Okay, so maybe then I'll erase the welcome part and write the title. So we'll talk about slowly getting into the topic, quantum topology at generic Q. So Q refers to a complex number, which will be a parameter of this entire story. And in early days of quantum topology, it's well studied, or reasonably well studied, well developed at roots of unity. So my goal in this lecture is to explain that something different and unexpected happens for generic Q, and the story is still in development. Many parts are developed, many parts require further development. So in that sense, it's on the cutting edge of technology. So part of my goal is to explain why is it interesting in the first place, what can be done, and then also present problems, what should be done and how we can tackle it in the future. So the main picture that will appear a lot in this mini lectures is picture for unit disk. So this will be in a Q plane, set of values of Q of absolute value less than 1 will play the central role. And if ever in the series of lectures or seminar you're lost, try to position present discussion, whatever happens in a given moment, relative to this disk. So sometimes we'll talk about things at generic Q. Sometimes I'll resort back to roots of unity, where I'll remind you of some existing constructions and various other things. So another basic ingredient, so one key player is going to be Q, that's the parameter. Another key object that was already briefly mentioned and will be mentioned even more is the quantum group. So that's denoted by Q. That's algebraic structure that we'll discuss perhaps in the second or third lecture. For now, what's important is that it's associated to a root system. I'll call it standard German or frac G, which is a Lie algebra of some underlying group. And even though in this lectures I'll probably say nothing about gauge theory, in various connections, this capital G is understood as a gauge group. So this is compact Lie group. And for most of what I'm going to tell you, the choice of G is going to be SU2. So the corresponding Lie algebra is SL2. And these are the simplest types of invariants that we're going to discuss.
Sergei, since there are mathematicians in the virtual room, the Lie algebra of the group SU2 is a Lie algebra SU2. SL2 is the Lie algebra of SL2. of a complex. So it's kind of bit higher.
That's right. So this is a little cavalier, but actually it will be important to me that right at the level of Lie algebra, they're really closely related. So indeed, maybe I'll write SU2 for now, but yeah, so that's a good point. Although later on SL2 will also come up. I have to say that anyway, yeah, I'll make comment about this later.
Yeah, all right. So I don't want kind of to be sort of a pest, but there is no quantum group UQ-SU2 by itself. It is, as in classical story, you have the complex Lie algebra endowed with anti-linear involution. That's the only way how you can speak about the Lie algebra of SU2. I mean, about the quantum group SU2.
Yeah, that's part of the reason why I wrote it this way, because, and also, first of all, yes, it's important to keep in mind this remark. Also, for example, WRT invariants that are at roots of unity, they're known in mathematics world for quantum group of 4SL2. So these are usually called SL2 invariants, whereas in Witten-Reshetikhin-Turaev's interpretation, they're associated with compact group SU2. So in that world, it's important that it's SU2. So there is, depending of whether you think about mathematical physics or quantum group, indeed, you would use either SL2 or SU2. And then it's going to be our job to relate it. Yeah. So.
Can I ask, so when you're talking in this discussion, are you talking about G, what is the field that G is defined over? Is it over reals or over complex?
So in on the right-hand side where I write capital G, it's important that it's over reals. I mean, it's a compact form. It's a particular real form of SL2C. So SL2C may show up later. So since you asked this question, let me write it like this. And it is a real form. So everything will be over the fields of characteristic 0, but whether we work sometimes over reals or complex numbers, so that will be important. So that will change. So, and in particular, what we're discussing now is to some extent the instance of it, because once we pass to the Lie algebra, everything is analytic. And in that case, when we work with this lowercase frag G, it won't really matter whether we are over reals or complex numbers. In fact, thinking about complex numbers being over C is more natural, whereas this SU2 obviously is a real form. So does it make sense?
Let me, since David is asking, so it's because it was a question long ago at the beginning of 90s. So if you speak about quantum group, and like these formulas of Drinfeld and Jimbo, which probably you will write next time. So you are talking about complex Lie algebras. They are complex numbers. If you want to speak about real forms, you mimic what you do without quantization. You consider a real group as a pair, which is a complex Lie group, and the anti-linear involution. So your real form is just a set of fixed points of that involution. So you change the involution, you change the real form. When you go to the quantum case, you do not have this option, so you have only quantized enveloping algebra over complex numbers. And so you should define by hand this anti-linear involution and say that the pair, if you kind of mathematician, you consider a category. So you consider an object which is a pair of quantized enveloping algebra of a complex Lie algebra and an anti-linear involution. And so that's, and then you can say that this pair is a quantized enveloping algebra of this real form, but there is no other way to say it. Yeah, so everything goes through complex numbers.
Yeah, so in quantum group world, it's definitely better to think about complex numbers. Again, that's what I was planning to do regardless. Yeah, so in mathematical physics, if you've heard about work of Witten on Chern-Simons theory, that's only for compact real form. So just to give, I'm not going to use much of it and wasn't planning to really, you basically expose one of the things I wanted to sweep under the rug. But if you hear about SU2 Witten's invariants and SL2 Reshetikhin-Turaev invariants, they're the same thing. I just wanted to let you know. I know it's a little bit disconnect and there is a reason to explain it or the way to explain it, but it's since we're fixing terminology here, it's I wanted to expose that it's the same thing.
Mm-hmm.
Okay, so right. Actually, given this discussion, most important perhaps thing is think about Carton type of the root system. So it won't appear too much in representation theory, won't appear too much in what we're going to do for general Carton types. So that's why I want to maybe say from the beginning that everything will be for type A1. So we'll do it for SL2 or SU2. Generalization to other Carton types is available, but will probably be outside of what we'll try to do. Good. So here we're introducing the key players. So one is parameter Q that's going to be central and appear in every single lecture. This root system is implicit, and I won't say much about it until opportunities arise, but it's going to be implicit throughout the entire set of 4 lectures. And perhaps another key player that I want to introduce is 3 manifold. So I'll denote it by M sub 3. So
sorry to interrupt you.
Yeah.
Do you want Q to be a possibility to be 0 or not?
Yes, yes. So we'll actually discuss what happens when Q goes to 0. It's actually one of the special values, very much like root of unity on the boundary of this unit disk. So yeah, so M3 will be closed oriented 3 manifold. Where the condition that it's closed will be soon relaxed. So in order for us to discuss cutting and gluing, we'll have to be able to consider manifolds with boundary. And I'll give you also basic introduction to AT's TQFT axioms and see how they apply in the present context. So these are 3 basic objects. Q is going to be our parameter, and we'll ask about analyticity. So the analysis will be with respect to Q. Topology will be with respect to M3, namely dependence on choice of 3 manifold. Sometimes in gauge theory, it's called capital Y. That's a very standard gauge theory notation for 3 manifolds. And dependence on underlying representation theory will be through this root system, which again, I'll suppress most of the time. So in this lectures, I'll try to construct certain invariants of 3 manifolds. So there will be roughly 4 elements, maybe very roughly, but that's not really my plan. They'll be associated to 4 lectures, but it's not really one-to-one map. So first, we'll start with a combinatorial and also then extend it quickly to diagrammatic construction. So First, we'll start with combinatorial construction, which is something very convenient and very friendly. So if you didn't have much exposure to three-manifold topology, this will be probably warm welcome and introduction into this very rich subject. So it will also allow me to introduce various notations and techniques without getting too far deep into the story. But to make it a little bit more general, we'll talk about proceed from combinatorics to diagrams, various planar diagrams. And this is where one of the key objects will enter, namely, we'll have to talk about our metrics for Verma modules of quantum group. And this will be essentially the first non-trivial representation theory element. So then in the second item, so this is basically outline of some of the things that I may cover, may or may not, depending on your requests. So as I already mentioned, I'll have to say a few words at least about the QFT structure, that's cutting and gluing in topology and quantum topology. And I'll try to give you another alternative definition of the same invariance based on a particular QFT called Rosansky-Witten theory. And Rosansky-Witten theory is a theory that depends on a choice of geometry on so-called target manifold or variety, and it has to be come with special properties. In particular, in technical terms, have to be holomorphic symplectic. We'll discuss this a bit later. So it's a interesting TQFT, or sometimes it actually doesn't fully satisfy axioms, so we'll need extension of TQFT. But what's interesting, we'll have to consider it on a very peculiar target manifold, or this choice of geometry, which has to do with cotangent bundle to the affine Grassmannian. I'll write it as T star of standard notation for the affine Grassmannian. So this is where some of the elements of geometry will come in particular, Rosansky-Witten theory has to do with derived category of coherent sheaves on this manifold variety. And those of you who are more inclined to think about geometric problems probably will have more fun at this point. And as you see, this is already getting progressively harder. So the next bullet point or item that, again, I may be able to cover is even more advanced. It has to do with enumerative geometry. And in mathematical physics, closely related subject goes by the name of BPS invariants. And both are rich and interesting. And what I'm going to tell you about can be viewed as a special chapter in that topic, where given a three-dimensional manifold, you can construct a Calabi-Yau space, three complex dimensional manifold, by taking cotangent bundle to a three manifold. And locally, it always admits perhaps incomplete Calabi-Yau metric in the vicinity of the zero section. And one can try to study enumerative geometry of this space. So I don't plan to say too much about this bullet point, but I want to mention it in the outline because it will come up depending on your requests in greater or smaller proportion. And another bullet point, which is also reasonably advanced, and again, I have some flexibility on how much to say about it, will have to do with so-called logarithmic vertex algebras. So this subject is interesting on its own right, because among vertex algebra, yeah, question?
No, I mean this Rosansky-Witten, which you mentioned, it cotangent bundle to a fine Grassmannian, it's infinite dimensional manifold. Do you mean QKFT on infinite dimensional manifold?
Well, TQFT is going to be three-dimensional, but this variety is going to be the target. And yes, the fact that it's infinite dimensional will essentially require most of our discussion, or yeah.
Okay.
Otherwise, it has maybe since you ask, I should mention that there are rigorous mathematical definitions of this TQFT due to Kontsevich. For a general target, which usually is assumed to be A, compact, and B, finite dimensional. So also Kapranov. So they go back to 90s and many others. And one of the interesting things that will make this theory interesting is that we'll need a version when not only this geometry is non-compact, it's also infinite dimensional. So we'll basically have to discuss how that changes anything. If there are new tools needed, but yeah, so that's going to be in some sense the most interesting aspect of this Rosansky-Witten theory. Otherwise, this is a TQFT which has by now 25-year-old history. So it's been introduced in 97, and I think, if I'm not mistaken, both of these papers I mentioned by Kontsevich, Kapranov, and others go back to 97. So it's been exactly 25 years. So good. That's roughly outline, or at least list of topics that will be our sandbox. We're going to play within this sandbox, and there are a couple of kind of parameters that I can change in our discussion. So one scale and knob that I'm happy to vary is the level of conceptual versus concrete material. So on one side of the scale, we can write conceptual. So these are general facts, theorems, motivation, where it feeds kind of discussion and so on. On the other side of the scale, concrete examples. In other words, when I'll be explaining how to do computations, maybe do one explicit example, and so on, that's where it belongs. So of course, every reasonable and good lecture should have components in both, and I'll try to strike a perfect balance, but I want to indicate that this is a dial that's flexible. That's something that you and I can vary. In fact, again, I encourage you to make requests, suggestions, and if at any point you feel that, oh, maybe it would be good to have more conceptual discussion, or you have specific conceptual question or a more concrete discussion, please ask. I'm a very concrete guy, so to me it's important that everything we're working with, we can really do hands-on computations, and it's as explicit as possible, so we can actually work with it. So another dial, I'll represent it as a round dial with various scales, 1, 2, 3, 4, and so on, is the amount of the physics content. So I'll try to keep it fairly low. But again, this is another dial that we can rotate and change. I guess I could introduce also similar knobs and dials. For example, I don't know interests of the audience too well. So some of you may come from algebra, some from topology. naturally, quantum topology is where these subjects meet. So again, I'll try to be somewhere in the middle, but if you feel that it would be advantageous, at least for some of you, or even for one of you, to move the needle one way or the other to clarify certain things, don't hesitate to ask. So that's, I mean, these are some of the knobs and dials that we can play with. Okay. So any questions about basic definitions, logistics, and before we get into, again, slow intro into the subject?
So far, there were no definitions, just logistics.
Mm-hmm. Yeah. So therefore, let's introduce, make one definition in today's lecture. So we'll try to associate to certain decorated graphs. So this is not a definition yet. I'm starting to set it up. So decorated graphs will associate certain integrals. Multiple integrals, which will have, which will be simplest example of the general story. But again, before we generalize, we should be able to start with simple families. And they'll also allow me to introduce more techniques from topology, algebra, and so on. So what kind of decorated graphs do I have in mind? So a graph is a collection of vertices, edges, and integer assignments to all the vertices. So in other words, a graph looks like this. So it's a set of vertices, edges, and also decorations. I'll call them A, which are integer valued labels of vertices. This is a function from vertices into Z. So that's what I'm going to call decorated graph. So in this case, the vertices could be A1, A2, A3, A4, and so on. Well, okay. So important piece of data to such decorated graph that we can associate is adjacency metrics. So now the first definition, which is very simple, is given, I'm not going to write the words, but I hope it's clear from the context. If not, tell me. But the words would be for decorated graph as above, which was already a definition, will associate a matrix whose size of square size, whose size is given by number of vertices, and matrix elements will be the following. We'll call this matrix Q. That's standard notation for this adjacency matrix of the graph. So we'll associate matrix element in slot ij equal to 1 if I and j connected by edge. So I guess I can write it as I and j form an edge, 0 otherwise. And if I is equal to j, then we have this set of values ai, which are integers. And that's precisely where it would be convenient to have some additional data, because obviously it's not very natural if graph doesn't have loops starting and ending at the same vertex to to put anything on a diagonal. So these AIs will play exactly this role, that there'll be diagonal values. For now, let's make a couple of assumptions, some of which I'll relax later. First, I won't allow edges starting and ending on the same vertex, precisely for this remark that I made a moment ago. Also, for simplicity, you may avoid even making large loops in the graph, but that's actually a very unimportant assumption. More important assumption that I'm going to make and use in a minute is that assume for now that Q defined in this way, in this definition, is negative definite. Okay. Any questions on this graph notations? So this is the combinatorial part.
Okay, so first line when I is not equal to J, and the last one when I is equal to J. So, or what? You said something about loops. I'm a bit confused. Because if you have loop, then I is equal to J. Yeah.
Okay, so first two lines are about I not equal to J, so I'll make it explicit. And right, so loops, there could be a couple of types of loops. So there could be this sort of loop starting and ending on the same edge, or on the same vertex, sorry. So suppose this is some AI, right? So this I don't allow.
You don't allow, okay.
Yeah, so something, in some sense, AI is precisely, has the meaning of something starting and ending on the same edge. But what we are going to allow and also use later if needed is something where a loop is formed by several edges, something like that. That's perfectly fine if this is part of some bigger graph. So this would be okay.
Mm.
Okay, so now we come to a more interesting definition. So we're going to
don't allow multiple edges between pair of vertices.
yes, for now, let's not do this. So indeed, allowing multiple edges is very similar to shooting a loop from same vertex to itself. And in a second, you'll see why this is not terribly important. So in other words, even if you want to start with something like this, there will be certain equivalence moves which allow you to resolve it into some graphs that don't contain such things. But again, for simplicity, we may just assume that we're dealing with trees, for instance. So that would be, for simplicity, that's in the beginning, that would be a convenient assumption as well. I'm going to relax it very soon, but that may be easier. Okay, any other questions? So we'll have this combinatorial data of graphs, or again, may think of it as trees decorated by integers assigned to every vertex. And to every such graph, we'll associate an integral. So that's now we're coming to more serious definitions. So previously there were just standard definitions of adjacency metrics and so on, but this is definition of an object that will be sort of central player or instance of a central player in our story. We'll define a class of integrals. I'll call them z hat. They'll be labeled by additional labels B, so that will be, I'll say what it is in a second. It will depend on such decorated graph, obviously, and it will be a function of our variable Q. So this whole thing will be defined as principal value multiple integral over all possible vertices. So for each vertex will associate an integration variable. I'll call it xi or xj. So product over j in vertices. Oops. dxj over 2 pi I xj. And then I'll insert some integrand that depends for each particular vertex we'll associate an in integrand. Also we'll do the same for edges. So we'll to every edge, namely a pair of I and j which are not equal in the set of edges, we'll associate also part of integrand and take product over all possible edges. And finally, the last ingredient, so that's a structure of this integral, will associate a theta function for the, which depends on all of our integration variables and is for the quadratic form Q. So that's where this assumption of Q being negative definite is convenient and will be used in a second. So in other words, what this is, so I'll try to zoom out on my screen because as you can see, this integral or this definition takes quite a bit of space. Yeah, that already takes it out of the page. Basically, we'll integrate as many variables as the vertices in this graph. For each vertex, there will be contribution to the integrand in the form of a multiplicative factor. For each edge, there will be contribution to the integrand in the form of the multiplicative factor. And we'll top this off, all this cookbook with theta function associated to the quadratic form. I already told you that we're integrating on a huge torus, which has dimension of the number of vertices of the set of vertices. For each of this integration variable, xi is xj, we're integrating on a unit circle. And if need be, use a principal value definition if there are any poles or singularities on this unit circle. But I have to tell you two things to make this integral meaningful and well, to finally complete the definition. I have to tell you what factor we associate for every edge and what factor we associate for every vertex. So that's what I'm going to do right now as part of this definition, namely for every vertex labeled by A. So vertex is represented in this graph by such bullet point or node. So to this, we'll associate a factor which depends only on the integration variable of that particular vertex. So it will be q to some power minus a plus 3 over 4. Maybe let me call this AI. So that's, I make it clear that it's an ith vertex. And then most important piece is that it will depend on integration variable xi in this form, xi minus 1 over xi squared. Okay. So then to an edge, which takes us from vertex I to vertex j, will likewise associate a basic building block in this whole integrand. So it will be inverse of xi minus 1 over xi. xj minus 1 over xj. So these are the two building blocks which respectively go into here and here.
So is b a non-negative integer or what?
Right, so I'm slowly, yeah, I apologize, I didn't get the chance to get to it. I had to unravel everything else. So defined in this way, b, which appears here, it only enters in the theta function. So theta functions have characteristics, and maybe I should write theta function more explicitly. So here, theta associated with the quadratic form q. Let me make everything super explicit. I was planning to write and didn't get a chance yet. So it will be sum over integers. Let's call them n. So that's a vector which belongs to q times basically a lattice with a quadratic form q. So its rank is the number of vertices. And then we can have characteristics in a theta function. So we're going to shift the summation by b. So b is a vector, and it enters naturally here, such that it's in a co-kernel of our q. Okay. If q is has zero determinant, so in other words has null vectors, then the corresponding there will be infinitely many b's, and we'll get to that. Again, in the beginning, if it's more convenient, you can also assume that q has a non-zero determinant. So then what is theta function? Theta function is q to something quadratic in terms of n, and multiplied by x to something linear in terms of n. More specifically, so q appears in the power minus n q inverse n, and then we have product over all possible values of I, xi to the power ni. Okay, so that's the explicit expression for theta function. So here, hopefully, it's clear that b is element of abelian group, namely co-kernel of this quadratic form. So, any questions?
So will you explain the strange factors?
Yes, yeah. So I'm glad you asked. So these factors look totally ad hoc. So natural question is, or to rephrase your question is, where do they come from? I mean, this looks very funny, weird. So what's so interesting or useful about them? Right. So that's the only definition and the main one I was planning to give for today. So let's, if there are no questions about whether this is, how it's defined and well defined and so on, play with this a little bit. I'll give you a theorem. So we have to learn some properties of this object. At least in this class of definition based on combinatorics of graphs and this data that we introduced. So I'll summarize these properties in the form of the theorem, which is goes back to work with Pei, Putrov, and Waffa. So it will have several bullet points, and I'll at least start summarizing them today, but I should probably, before I do that, also mention that there is a closely related work by Catherine Brinkman, Karl Malberg. And Anton Milish. And also my work with Ciprian Manolescu, where you can find various alternative ways or ingredients in proving this theorem, which will have many bullet points. So I'll come back to this theorem in a second, but as a first bullet point, I want to say that this object, this set of integrals, as a series in Q, so it depends on choice of this graph, and is a function of Q. So first statement is that it converges in Q inside the unit disk, but not on the boundary. Okay. So this you can show, for example, it's not very hard, and essentially even the ratio test for the coefficients that you get for this series will show you that it converges inside the unit disk. We'll come back to this item because first I present it as an integral, but then later on, perhaps in a second lecture, or even later, I'll try to rewrite it in a different form. So it's not really, I mean, this expression can be understood, or this rather complicated expression has several incarnations, and I gave you one, but later I'll try to write it as a sum, and in that format will be basically reproving this statement or giving arguments that are essential to it. So also at this point, we know that this label B takes values in a co-kernel of Q. So I'll leave some room because later on I'll try to return to this statement of this theorem and give it alternative interpretation.
Sergei,
Yeah.
I'm a bit confused. Your graph is finite, yeah?
Yeah.
And your formulas, Q enters in the formulas only for the factors associated to vertices. Okay.
And theta function.
But theta is convergent, or it's not.
Theta is convergent, so that's where notice that Q, little q, used minus something quadratic and Q inverse n. So if so, that's, I mean, there are various sign conventions, but with the sign conventions as written here, if Q is negative definite, then it will be expanded in positive powers of Q. So that's where this negative definite was useful assumption.
Okay, all right.
So on the screen sharing, it's this part.
Okay.
Yeah. So
the Bardinian form on this exponent of Q, that's just the standard products.
Exactly. Yeah.
Okay.
Yeah, there are several ways of writing these theta functions. Yeah, so of course, equivalent way would be to get rid of the Q here, and then it will appear here as n Q to the +1 or the -1, and so on. But then characteristics would enter in here. So yeah. But yeah, so conceptually, what's important is that with this minus sign here and Q negative definite, this is expanded in positive powers of Q. And the structure indeed is of this whole thing is we have convolution of theta function based on our quadratic form with some rational function, because all these factors, notice they're rational factors of integration variables xi. There are just too many of them, I mean, for generic graph. But other than that, that's the structure. And next time, we'll talk a little bit about structure of such integrals, what kind of things they are. So for now, as a function of Q, what we see is that, again, it converges inside the unit disk, but not on the boundary. So that's important. That's can be again done by this ratio test and so on. Also, as a function of Q, what I'll show you in a second is that, right. Oh, by the way, I realized that I already exceeded my time limit, right? So we're approaching the top of the hour, basically. So maybe, Jan, you're the chair. So is it a good place to stop then?
Well, it depends. If you can formulate in 1 or 2 minutes the rest of the theorem, that's okay, but you can continue on Wednesday, so it's up to you. You don't have too much time, this is true. So just maybe a couple of minutes to finish if you have.
Well, if I have a couple of minutes, let me do the following. So I was planning to, so this theorem will take some time. So that definitely I don't want to do today. But one thing I was going to do is to show you the explicit computation of this integrals and also share the software that does it. So in fact, that's a good opportunity because then by Wednesday, you can play with it yourself. So what I'll do next time, I'll start with this Mathematica code and I'll run it for you. Basically, it allows to enter the data of the graph. So here is this example of a graph with this integer decorations. So it will check several things, including the negative definiteness. So there are some eigenvalues here. So since we made this assumption, we'll make this check. It does some computation and produces an answer which looks like this. So since, again, I want to make everything super clear, explicit, I don't want to rush right now, but what I'll do, I'm going to share the link to a web page, my Caltech web page, where I uploaded this Mathematica notebook. It's very short, very simple. I'll repost it again next time when we'll experiment. So our job will be to learn what kind of object we just introduced as a function of the graph. So it's easier to describe what properties it has as a function of Q, and I'll come back to it. But one thing that we'll do using this Mathematica file is to play and slowly learn how does it depend on a graph, and that's going to be a lot of fun. And I don't want to rush through this fun, so we'll start with it on Wednesday then.
Okay, but will you explain kind of the motivation for those factors, rational factors?
Yeah.
Everything looks mysterious. Yeah.
Yes.
Yeah.
And of course they are. Yeah, right. So as promised, again, we're moving extremely slowly. So I can only do little steps at each point. I cannot do everything at once. So again, if there are some things which are more interesting than others, like on this conceptual concrete dial or algebra versus topology, please make suggestions, let me know. So I'll definitely come back to question where this all comes from and what's, so in some sense.
Yeah, as a mathematician, I would prefer to understand the concept, then it will be easier to follow kind of concrete examples and whatever programs, because just numbers by themselves, they kind of, at least for me, they don't convince me. Yeah.
Well, at this point, this is not supposed to convince anybody of anything. It's just introducing an object which has lots of properties, and theorem that I started stating will have 4 or 5 bullet points, which are important properties. So at this point, we didn't even finish defining it yet, but we'll do it little by little, very, very slowly. Again, if you want me to speed up, I'll be happy to do it. Yeah.
All right. Maybe we have time for one short question, if there is one. Anyway, just first lecture.
Let me quickly ask a quick question. That was Jan's question earlier. So in cases of the graph is finite, and when you said series is not convergent on the boundary, which if all the exponents of Q are non-negative, so that should be almost it's a polynomial of Q, right?
No, not at all. So again, I don't want to rush through this, but it's going to be it's going to be Q series with certain properties. In fact, collection of Q series, as many as elements in the cokernel of the adjacency matrix. So we'll play with this next.
I see that's an infinite
time.
sum over there.
Yeah, the theta series is already sum.
That's
But then,
okay,
then you integrate, the integrand converges, but when you integrate, it can be a mess.
Yes, exactly.
Theta is an infinite sum. Thank you.
Yeah, already in this, from the viewpoint of topology, you'll see that we're just starting in this class of examples, and we'll generalize it to generic three manifolds. But already here, there'll be a fun analysis in terms of Q dependence, namely some estimates, in particular in regards to questions like this. And yeah, I'll also have to explain how it really depends on the graph, because that's where a lot of
another question.
Probably you want it not to be very much dependent, because this graph is related to some three manifold, to the way to you glue your three manifold or something like that.
Yeah, that's exactly what we'll have to learn slowly. And yeah, again, I apologize if some of this is a bit too slow for some of you. Feel free to tell me to speed up or make suggestions. Like, for instance, given Jan's suggestion, I'll definitely, once I finish this theorem, which will take some time, but then I'll go to concept. And next time we'll talk about conceptual things, including where does this come from? Yeah.
So does the Z gives the theta function of counting something?
Well, from the bullet points that I mentioned in the beginning, you can probably anticipate that it is counting something. In particular, it's counting. It has interpretation in this world of enumerative or BPS invariants. But this, so the answer is yes. The short answer is yes. The longer answer is probably going to be on Thursday. So this is more of one of the deeper topics in this story. Yes.
Okay, we'll be looking forward to. Thank you.
Okay, thank you. And
thank you all.
Okay, and so see you on Wednesday. Yeah. Okay. Спасибо, Сергей. Okay, thank you.
Спасибо.
Все, пока.